Hello guys, in this video I'm going to talk about the Bayesian parameter estimation. So let us see what is parameter estimation. So in the first video I talked about the likelihood being a continuous distribution, a PDF, probability density function. So we talked about how do we get this. So I told you that there are these samples. So basically what do we have with us? We have only the samples, the data samples. So in our example we just have these images. We just have the images and we have to figure out from these data or these images what will be the PDF of this likelihood. So we just have these datas and we have to figure out the PDF. So then we also looked about the Gaussian distribution. So we saw the multivariate Gaussian distribution, we saw the univariate Gaussian distribution. So we came to know that to get the distribution, we only need the parameters. If suppose we have these parameters, we can put the parameters in this formula and we can get the whole distribution. So now our task is going to be, we want to find out the parameters. Say for the Gaussian distribution it is going to be mu and sigma, or the mean and covariance matrix or variance for a univariate case. So we have to find out these from the data. So this is the task that we have to achieve. So let us go through it and let us see how can we achieve this task. So this is our normal Bayesian rule. It says that the probability that it is some class I, so in our example it can be sunflower or rose, so probability sunflower given that some image, so this is nothing but the test phase, is equal to probability of, you have to find out the probability of the particular x. So we talked about this, that say x is the size. So what is the probability that x is equal to 6 given that it is sunflower? So this we are taking from the training. So this we have the training. So we are now going to focus on the likelihood only. Into the prior upon the evidence, we normally remove the evidence because it is just a scaling factor. So let us see what is the Bayesian parameter estimation. So let us consider the whole set of images. Now I have these many n1 set of images of say sunflower. So sunflower is one of my class. So I have n1 images of sunflower and say I have n2 images of rose. So let me denote d1 as this whole set. So this whole complete set of images is denoted by d1. This complete set of images is denoted by d2. Now next, like this I can have m number of classes. So there can be sunflower, rose, lily, lotus, etc, etc, etc. So I am denoting it as m. So there are m classes, there are m flowers that can be classified. Now for every class, say for every sunflower, I have a particular set of image. So this first image belongs to this, second image belongs to this, and every image will have a feature vector associated with it. So this image will have a feature vector size. So that say x1, I have denoted size with x1 throughout my lecture series. So let x1 of this image, let it be 6. So the image distance from this is 6. The radius that we have taken so long is 6, and the other parameter also that we have found out. So this so let us consider a univariate as one feature case for now, then we'll generalize it. So there is this feature. So these are nothing but the x1s for the first feature. So xi1 will be 6, xi2, say for this, what is the size for this particular image, so let that be, say x1 is equal to, say 7. So xi2 becomes 7. So these are what? These are the size of different images that we have in the data sunflower. So this, so we saw that we have, say n1 images, so we'll have n1 feature vectors. So for every image we'll have one particular size, right? So the number of images are equal to the number of features. So we have, so for n1 for d1, so like that di ni for ith class, right? Now these are parameters that have to be estimated. So for a Gaussian case, so here there is an assumption, we are assuming that the likelihood, it follows a Gaussian distribution. This is an assumption that we are making, that likelihood follows a Gaussian distribution. This may or may not be true. So we discussed in my univariate Gaussian lecture that we take Gaussians because of some of its advantages. So this holds good when we take the distribution as Gaussian. Okay, so like that, it is not necessary that you always take Gaussian. You can take any other distribution that you want. So for other distributions, the parameters may vary. So Gaussian distribution is a simple distribution which has just two parameters, but then there are other distributions which can have 3 or 4 or 5 parameters. So let in general, any distribution that we are assuming, so this I am taking a general case, so we can assume any distribution for the likelihood. So in general, I am taking k parameters for a particular distribution. So in case of Gaussian, this k will be 2. I will just have 2 parameters, that is the mean and the variance. So k is the total number of parameters of the distribution. So different distributions have different number of parameters. So now what is our task? So we have to find out what are the theta i's. So we have to find out this theta 1, theta 2, theta k. So in case of Gaussian, we'll have to find out what is theta 1, that is mu, and what is theta 2, that is covariance. Only two parameters is what we have to find out by the data. So we are given by the input this, we just have this data and we have to estimate the parameters. Why we have to estimate the parameters? Because if we know the parameters, we know the distribution. So we saw that this is the formula of the distribution, say in this case Gaussian. So if we know mu and sigma, we know the distribution. All other things are known to us, so we know the distribution. So that is why it is important to just estimate the parameters of the distribution, and we can have things done. So I'll repeat myself. We have the data, we just have the data, and we have to estimate what will be the parameters mu and say variance in case of a Gaussian, or in general what are the k parameters of any distribution. So that is what we have to do. So now we'll proceed with some assumptions. So one assumption is di gives no information about theta j. So what this says is that this data of sunflower will give no information about the mean of the rows. So that is an assumption. So now this may or may not be the case. So there can be some classes where the data of one class is affecting the mean of the other class. So in most of the cases, this assumption holds, which is true, because the data of sunflower will never tell you something about the mean of the rows, or the data of rows will never tell you the mean of the sunflower. So in this case it is true, but in some other cases this may not be true. So we are going with this assumption. So when we go with this assumption, so we can say that di, So we can say that theta I only depends on di. So the mean of this sunflower depends only on the data of the sunflower, and the mean and variance of rows depends only on the data of rows. That is what we can say. So now let's go further. So here what we are going to do is, we have this data. So let's say this is my x1, which is giving you the size. So I've talked about what is the size. So what I'm doing is I'm plotting the size on this axis. So say first I got here I got x1 is equal to 6, so I've plotted that. For the second image, say I get it some 7.1. For the third image I get some 5.2, 5.1, 5.0, 4.9, like this, like this, like this. I've plotted all the data that has the features that I've got from this image. This I've plotted. Now we just have these dots, we have these datas with us. What we have to do is, we have to fit a Gaussian. So here I am taking Gaussian because we have become familiar to a Gaussian. So we have to fit a Gaussian such that it is approximating our data. So intuitively speaking, you can see that a lot of data are falling in this range. A lot of data are falling in this range. So you can say the probability of the data falling in this range is higher, because a lot of data samples have come over here, and you can see only two data samples have come over here. So the probability of data coming over here is lesser. So what we actually are going to do is, we are going to see, say in this case I am just considering the mean. So mean is one of the parameter of the Gaussian. So we are going to change the mean. So we are going to have mean as variable. We are going to see if mean is equal to 1, is this holding true for the data. So is this distribution holding true for the data? We are going to see. Then we are going to put mean is equal to 2, 3, 4, 5, 6, 7, and we are going to see which particular mean is going to fit the data. So for that, what we'll have to do is, we'll have to calculate the probability of a x. So what is x in this case? This value is x. So let me I'll show you how this happens. So let us consider, I am considering this x. So you will basically take the mean is going to be a variable over here. So first I'm taking mean is equal to 1. Say let me take mean this. So this is the Gaussian that we have. So if the Gaussian is this, I'm going to calculate what is the probability of this data. So the probability of this data will be something like this. So this will be the probability of this data. Then I'll move the mean further. So I'll change the mean. I'll have this mean, and I'm going to see what is the probability. Then I'm going to change the mean and see some probability. So this is what I'm going to do. So this I'm going to do for every sample. For every sample I'm going to do this. So there is another assumption that we are making, that samples are independent of each other. So that means this sample is 3. So this sample does not give you any information that other sample will become some 4. So that basically says that if I got x is equal to 6 over here for this image, so I still have no information about what will be the value of x in my next image. So that means that both of these are independent. I cannot predict anything about the next image by just the information of this image. So this is also assumption that we are making. So if this is true, so then the probability of the whole data set having parameter theta I will be nothing but multiplication of all probabilities of every sample. So let me again just make you visualize what we are doing. So we took this probability. So for say for one, say I took mean is equal to 3 now. So I am taking mean is equal to 3. So when I take mean is equal to 3, I will get some this kind of Gaussian, because so I'll get some this kind of Gaussian for mean is equal to 3. So for this sample, this probability is going to be highest, so that I'll write somewhere. So say this probability is highest, so this is say some 0.7 suppose, so this I'm writing over here. So next, then I'm going to calculate the next data's probability with respect to this Gaussian. So here you can see this is the probability, so this is somewhat say 0.4. Then I'm going to calculate the probability of this sample, that will come here into this, into this, into this, into this. So you can see there are datas over here. So because of this data, say over here, the data over here, there'll be one case where I'll get probability say 0.00001, something like this. So I'm taking this Gaussian and calculating the probabilities of every sample. So for this data, the probability will be very less for this curve. So the final answer will be very less. So final answer will be, because this is tending to 0, so the final answer will be say something 0.0001 something, or make it 2. So this will be some final answer. So you can see that yeah, this particular thing cannot be the good Gaussian approximate for the given data. So next we'll do this for every particular value of mean. So next what I do is, say let me take a mean of say this mean of say 4.9. okay, so I get this Gaussian by this particular mean. Now what I am going to do is again going to calculate the probability of every sample. So this will be say some 0.2, so I am having 0.2 over here. Then this is some say 0.7, some 0.8 I guess. Then there is something. So you can see for this Gaussian, mostly all the points are lying inside the Gaussian, all the data samples are lying inside the Gaussian. So this will have some probability which is much higher than this probability. So the mean being 4.9 will have a greater probability than the mean being 3. So this is what exactly we are doing over here. We are going to multiply. See, we are multiplying the probabilities of every x given a particular mean. So I fixed a mean, so I am giving the mean, and what I am going to do is I am going to calculate the probability of every data sample with respect to that mean, and I am multiplying it, so hence there is a product over here, and I am multiplying them for every sample. So there are say n samples, oops, there should be ni. So we have ni samples, n1 sample for data 1, n2 samples for data 2. So we have ni samples for data I, and the whole probability that this data belongs to this particular given mean is calculated like this. So now if you see, if you plot theta on one axis, so I am plotting say mean over here, so on one axis, and I am plotting this probability of di given theta I. So you will see that we saw in this iteration over here, for mean is equal to 4.9, we got a good probability. Say these are big numbers, because everything, say this will also be say some 0.1. It will not be like the previous case where it is so far away from the mean. So this you will get say something 0.02. So whatever this may be, this will be higher than any of the mean that I calculate changing the means. So if you take a Gaussian like this, so you can see there is this data sample which is very far away from the Gaussian, so again the probability will go less. So this is essentially a graph that you will get if you plot mean versus the probability that the data I follows that particular mean. So for this this mean which takes maximum data into it, So it is like taking maximum data into it, I will get a good peak, and for others I will get low probabilities, and as I go away from the actual true mean, the probability will just reduce to zero, because any particular term giving value very close to zero will make the whole product zero. So this is what I am going to get. So please understand what is happening over here. Now sometimes what happens is, if suppose you have a large data set, you have a very large data set where say you have samples distributed all over here, so still the frequency of the sample may be high over here, because it is it is by definition that the frequency of the samples along the mean will be higher, and as you go out the frequency will reduce. So if suppose you have some data sample over here, if suppose you have some data sample over here, so this, in spite of being a best fit, so this is taking maximum datas into it, in spite of it being a best fit, since this is still far away from this, will give you a value something like this 0.001 or something, which will in turn, when multiplied by other probabilities, so even if one probability is 0 in this case, the whole multiplication becomes 0. That is the problem of multiplication, because one anything into 0 makes it 0. So this is one of the problems that we face, that as soon as we increase the data, and if say even one data comes very far to the mean, which is quite possible because Gaussian is an infinite curve, so it goes from minus infinity to plus infinity, so there is some small probability that we can get a point like this. So because of this, the whole probability tends to 0 and we get a flat 0 curve, which is a wrong thing, right? So what we do is, instead of taking the probability, if we could, because the problem is with this multiplication, so if we could convert this multiplication into summation, then our things are done. So for that, what we have to do is, we can take the log. So if I take the log of this probability, I can convert this summation, this product into summation, and now even if a value is tending to 0, because of this sum, the whole function will not tend to 0. And let me show you how will that graph look like. So if I am plotting theta with respect to log of probability of di given theta, then I'll get this sort of graph. So here you can see that here I am getting low values, just because if something tends to 0, then the whole function will tend to 0, because I am taking a product. So we are getting a curve like this. But here, since if something is tending to 0, the function will not tend to 0. It will just ignore that thing basically, because say 1 plus 0 is just 1, it will just ignoring the 0. So hence we are getting a curve like this. So in cases for where the data samples are very apart from each other, we take log, which is a good thing. So now here also we have a peak. So this will again peak only where with the mean of the Gaussian taking all the data samples inside it, maximum, not all, maximum of the data samples inside it. So this is the plot we get. So I guess this is enough for this video. For the next video I am going to so this was a generalized thing. So I just gave you this visual representation using Gaussians, but then I could use any distribution over here with any parameter that the distribution has. So this was the basics about the Bayesian parameter estimation. So in the next particular video, I'm going to talk about what is the maximum likelihood method, and we will see how does that go. Thank you so much for watching. Thank you.